We will cover nuclear chemistry. This is chapter 21, the last chapter of general chemistry. Nuclear chemistry is the study of reactions that involve change in the nuclear structure. An unstable nucleus is called radioactive. First, we will start by reviewing atomic notation. So, any atom is usually denoted as X, which is a chemical symbol, with Z on the bottom, the atomic number or number of protons, and A on the top, the mass number, which is number of protons minus the number of neutrons. Another notation is X-A, because for each X, Z is set, meaning that atomic number determines the identity of the atom and therefore the chemical symbol. In the nucleus, we have protons, neutrons, and electrons. Protons have one proton, just standard one proton, and have a mass of 1. Therefore, for instance, hydrogen has 1 proton and a mass of 1. Neutrons have 0 protons, but they have a mass of 1, and electrons have a negative 1, but they have a mass of 0. Some particles that we need to examine are alpha particles, beta particles, and gamma particles. Alpha particles are positive, beta particles are negative, and gamma particles are neutral in their charge. Their penetrating abilities vary. This is often tested, so it's important to remember that gamma has the highest penetrating ability, beta has low, and the alpha has the lowest penetrating ability. I like to remember it through this diagram. Here. Nuclear reactions. They are reactions where atoms are typically consumed to different elements because of the atomic number change. And reactions have a large change in energy and some changes in mass. So for instance, an atom goes from a parent nuclei, obtaining a parent nuclei to a daughter nuclei. Some energy is released and particles are released, leading to a change in energy and a change in mass. It's important to remember to analyze nuclear chemistry, remember the particles and their symbols. So the first is alpha particles, which we use the symbol alpha, and we can use a hydrogen. So they have an atomic number of 2 and a mass number of 4. Beta particles have an atomic number of -1 and a charge of 0, and a mass number of 0. Gamma particles have 0 atomic number and 0 mass number. Positrons have +1 atomic number and 0 mass number. Protons have a +1 mass number and +1 atomic number. Neutrons have a 0 atomic number and +1 mass number. While protons and neutrons and alpha and beta particles can be easy to remember, it's important to remember that positrons, the distinction between positron and alpha particles, and so on and so forth. Some associated things with each of these particles is alpha decay, beta decay, gamma ray emission, positron emission and electron capture, and proton emission and neutron emission. We will go over each of these in detail. Nuclear equation is this, where a parent nucleide goes to a daughter nucleide plus a particle. And on top of each one, we write the mass number, and at the bottom, we write the atomic number. The rules for balancing them are that the sum of the atomic numbers and the mass numbers must be equal in each side of the arrow. Alpha decay is the emission of alpha particles or the He helium nucleus, and it is very common with Z number, meaning the mass number greater than 83. Here we can see the alpha particles are written like this, with a helium or with an alpha symbol, with 2 at the bottom and 4 at the top, meaning 2 is the atomic number and 4 is the mass number. And here in this example, we see that the Pu is split into the alpha particle plus a new changed daughter nuclide. And this changes the identity of the atom. A beta decay is the emission of a beta particle. A beta particle, as we reviewed earlier, has an atomic number of -1 and a mass number of 0. It can also be written as an electron. And here we can see the same thing, where a carbon is broken down into a beta particle and a nitrogen molecule as the daughter nuclide. And here we can see at the bottom that the 7 plus the -1 leads to 6, and 14 plus 0 leads to 14. And this is how both the atomic number and the mass number have been balanced. A gamma emission is A gamma, again, as we had earlier, it has a mass number and a charge number of 0 and 0, so it does not affect the identity of the atom, but it is a form of electromagnetic radiation, and what it does is changes the nucleus from an excited state, as indicated by this star sign, and decays it to its ground state with no star sign, and is also emitted along with other types of radiation. So here we can see how barium in the excited state is transferred by the emission of a gamma particle into barium in its standard state. Positron emission. Positron is this. Positron is basically the opposite of an electron. It has a mass number of +1 and an atomic number of +1 and a mass number of 0. The emission of a positron can be seen as this, where an oxygen is broken down into a positron and a nitrogen molecule because of the +1 in the positron. Here we see an electron capture. It is important to remember that it is capture, meaning it is added to the reactant, and therefore we see the electron in the reactant side. Here we can see it this way, and an electron is written like this, where with a atomic number of -1 and a mass number of 0. And here we see this on the reactant side and how it's balanced at the bottom, and how the potassium turns into argon. Proton emission is written like this. It is the emission of a proton, and it's very rare. It is basically a mass and atomic number of 1 and 1. And a neutron emission is the emission of neutrons. It occurs in the neutron-rich nucleus, and it's fairly rare. We can see it as this, as neutrons have a mass number of 1 but have no atomic number. Now we'll analyze the kinetics of radioactive decay. All radioactive decay occurs via first-order kinetic. In a nuclear reaction, consider the rate-based number of the nuclei, A, present. So, like we said, it's the first-order kinetic. So the rate is K times A. Rate law is ln of A at T is equal to minus KT plus ln of A at 0. And the half-life, or T at 1/2, is ln of 2 over K. To break down some of these variables, K is a rate constant that is experimentally determined. A0 and AT, A0 is time 0 and AT is the time designated, and it is the number of radioactive nuclei in grams, and time is T, T1/2 is half-life. Nuclear fission is the splitting of heavy molecules into lighter ones, and nuclear fusion is the combination of two light nuclei to form a heavier one. And they both release enormous amount of energy, but fusion releases more energy per gram than fission.